So I think the search for exoplanets has been quite motivated by our desire to find life in the universe. This particular paper I'm referring to, sorry, it didn't come out very well in the slides, but it's a paper from the 70s that is a visionary one that is basically putting forward the idea that we need to find extrasolar planets, both for understanding how planets are forming, and so planetary science more in general, but also as a way to philosophically address the question of life. So the good news is that since the 70s, we made a lot of progresses, and now we do know that planets are ubiquitous, so we're expecting billions of planets in our galaxy alone. And I think, again, if you're interested in life or habitability in general, the fact that many planets are relatively small, it's a good news. Certainly, this is something that we didn't expect before a mission like Kepler could fly. And Kepler in particular nowadays tests, but also other facilities from the ground doing microlensing or radio velocity are telling us that basically in particular planets in between the size of the Earth and the size of Neptune seems to be very common out there. And so again, this is fantastic because it's opening up a lot of opportunities. And the talk from Madhu before was in fact trying to point out that perhaps we shouldn't really fixed only on the twin of the Earth. There are many other potential examples of potentially habitable planets out there. We have also already excellent opportunity to go after, in a certain sense, what I would call the low-hanging fruit, not because they're not interesting planets, but simply because it is a fact that through the transit technique nowadays, we can already look at relatively small planets, in particular around cool stars using the transit technique, and some of these planets are in the habitable zone. Are they habitable? Of course, we don't know. That's why we need to observe. Already Hubble started to give us some hints, in particular in a few examples, in particular for relatively small planets, this sort of hybrid planets that we don't know too much about, whether they're super Earths or some Neptune or ocean worlds. But still, the fact that already with Hubble you can say something, and clearly this is fantastic territory for James Webb. That's where James Webb really will give, I'm sure, really surprising results. But of course, as was mentioned also by Sasha in the previous talk and Rebecca, transiting planets are great. They give us a view about, in particular, the habitable zone of later star or cool stars. But if we want to be a bit more generic, if we want to study habitability in a different parameter space, in particular of star more similar to the sun, that's where direct imaging really needs to give us these targets and also the opportunity to study them. And as an astrobiology fellow 20 years ago that was working on terrestrial planet finder, clearly the news that in particular NASA is putting a lot of efforts to develop the new generation of this habitable world observatory, and both the Decadal in this country and our roadmap by ESA astronauts on the other side of the pond are pointing out that this is really an endeavor that we want to have as the next step. This is absolutely fabulous. And clearly the role of flagships in order to tackle this important question, this a complicated one, is absolutely critical and crucial. But also what I want to advocate perhaps today is the need, in addition to these flagships, also of an entire ecosystem, both from the ground and from space. In particular, we'll focus a little bit more in space here, of satellites that are small and moderate size, but also facilities from the ground that similarly have different sizes and complexity. Because at the end of the day, we need this ecosystem. We don't want to, as exoplanetary scientists, have just one observatory and work everybody in this sort of monoculture. We don't want that because it's in our DNA. Extrasolar planets have been thriving because so far we had many techniques, different way of looking at a different parameter space, and this has been a great success. So in my view, we should really keep this ecosystem. And so I also want to remind perhaps everybody that, again, we certainly want to have this very performing mission as a next step forward, but again, in exoplanetary science, many of the great discoveries in the end were made with very modest facilities. And just picked two examples. 151 PEG-B, awarded with a Nobel Prize to Major and Colosse. Again, very relatively small facility from the ground. But also the TRAPPIST-1 planets that are absolutely so fabulous, and we all want to study them with James Webb, the 7 planets that are transiting around this cool star. Again, it was obtained with a relatively small facility. So again, I think we really need to bear this in mind, in my view. So talking about moderate size facility from space, I would like to have to talk about Ariel for a few minutes. What is Ariel? Well, Ariel was selected first and then adopted by the European Space Agency in 2020. We just passed the PDR, and so we are going towards the next milestone, which is the CDR in 2025. And so far, we are well on schedule for launch in 2029 in L2. So we're talking about a 1-meter class telescope, and the unique selling point of Ariel is to be able to cover simultaneously wavelengths from the visible down to the infrared, going from 0.5 micron in the visible down to 7.8 micron. Why we want to do that? Well, because what we're aiming at is not necessarily aiming at observing spectroscopically a few individual planets. That is clearly something that you can do, in particular with James Webb, but perhaps also with our facility. But the unique selling point of Ariel is to try to have the big picture. So going for the large number of exoplanet atmosphere being observed. We're talking about hundreds, well beyond 1,000 exoplanets being observed. And we want to include in this sort of census both rocky, but also giant planets, anything in between, around any type of stars. The idea of Ariel is really try to do as much as possible a sort of homogeneous census of atmospheres of planets in the solar neighborhood, and try to understand how is changing the chemistry with basic parameters involving the temperature of the planet, the size of the planet, a type of stars, metallicity of the star, and so on and so forth. And if we can think of a relatively unbiased sort of sample, then we hope that then this will tell us basically what is the sort of normal behavior, chemically speaking, of the planets in our neighborhood. The Ariel Consortium now is including more than 400 scientists and engineers from 16 ESA countries. And we have a contribution from NASA, from JAXA, and from the Canadian Space Agency. The consortium is building a great part of the instrument, but also the telescope, whereas ESA is providing the spacecraft. The spacecraft is actually built by Airbus. And also the operation and the launch will be provided by ESA. So it's clearly a large consortium, but it's great because we have really opportunity working together and have many contributions coming from many countries. So focusing a little bit on the targets that Ariel will look at, and I'm focusing here not on the planets, but on the stars, so the stellar host. So many of the targets that we are currently including in the catalogs of potential targets that Ariel will look at are coming from TESS. TESS is fabulous for us because focusing on very bright stars, clearly the brighter are the stellar host, the more we can extract out of the planets. So Ariel has really been conceived and built to focus on very, very bright sources. And so for the moment in the current catalog, as you can see here, we typically can look at stars with a distance up to 1,000 parsecs roughly. Of course, it depends on the type of star. And also, clearly, we want to have stars of different type. The parameter I'm selecting here to look at the type of stars is the temperature. But again, we want to make sure that the sample is as complete, as diverse as possible in order to address all the questions that we want to have. For the planets, I'm going to focus here only on small planets for obvious reason, given the focus on habitability. So even for planets that are relatively small, and including here among the targets that we're looking at, targets that are smaller than 3 Earth radii and a number of temperatures, again, TESS is providing really a lot of potential targets. I think in terms of contribution of aerial to habitability, in my view, more than the focus on perhaps being able to look at habitable planets per se, I think where really area will be give a strong contribution is to more the understanding of non-habitable planets. And why is it important to understand non-habitable planets? Well, it's important because if we want to understand, to start with, what a biosignature is, do we really understand so well the entirety of this equilibrium chemistry in atmosphere that are so different from the one we know? Clearly, at the moment, we don't necessarily have a standard model of planets in the galaxy. We need to have a very large sample of the chemistry of these planets before we can really understand what's going on from a chemical perspective. But also, it's an excellent opportunity, in particular, if you're focusing on relatively warm and hot planets, to understand better the interaction between the interior composition and atmospheric composition, something that we all know that must be very important, in particular for small planets. These are complex objects, not like the giants. And looking at planets where the temperature is relatively hot, it means that the atmosphere becomes much more easily the window of what is happening in the interior. So again, Ariel is offering us an experiment to understand much better non-habitable world. And I think then it will be probably easier to understand habitable one for the next generation of mission that will come after. Before I close, I also want to just spend a few words, in particular with this idea of an ecosystem that, in my view, is needed from the ground and from space, about new opportunities, in particular in space. I love the talk about Tolliman that was showing how far you can go, how much you can push with a relatively small satellite, really addressing very high risk, high gain question. That's why I think it is important to keep this ecosystem. And analogously, in London, we have Blue Sky Space. I am one of the co-founders of Blue Sky Space, and we basically pioneered the commercial approach in order to look at the delivery of high performance but relatively small and moderate size scientific satellite to the global community. And so the entire idea behind Blue Sky Space, again, in parallel to the great efforts that are being done in more government sort of funded big satellites, to contribute also from the commercial world, from the private world, in being able to build even more satellites, address even more scientific questions. We are of the opinion that the more the merrier. And there's an entire global community that are really looking for this data. And so in our vision, at a certain point, we will have already a large fleet of satellites, but for the moment, we have two that are ongoing, and MOV in particular that has been very recently started is a 16U CubeSat to look at stellar flaring and activity of M-dwarf or other stars, with the idea really to monitor the activity. And the idea in particular, if we're interested about the habitability of some of these words around M-star, to work out whether they're really very active, the stars, if they're flaring or not. Could be really very good opportunity to study many of these words. Bigger one is Twinkle. It will be built by ABB and Airbus. We are talking about a small sat in this case and has more spectral capability, more in the visible and the infrared. I'm cautious of time here, and so let me start to wrap up some thoughts to conclude, and I hope that some of these thoughts could be a good inspiration for some discussion after. So the search of exoplanets certainly has been driven, at least partially, by our idea, goal to discover life in the universe. And nowadays we know there are billions of planets out there, and small planets are actually very common. And this is a great news if you're interested in habitability. There is definitely hope that we can address this question properly in the next decades. The fact that we have all this diversity in terms of planetary systems, in terms of orbit, stellar type, planetary characteristics, I think is not only something that was unexpected and, in my view, quite interesting, but But also it offers us really the opportunity to address the question of habitability from many different perspectives. And so it's really challenging, in a certain sense, our geocentric view of how habitable world must be looked. Again, a reminder to all of us that great exoplanet discoveries were obtained, in many cases, with a relatively modest facility. And so, again, it's very important, again, in my view, that while in the future we're looking at this fantastic opportunity with big flagship missions and even big observatories from the ground and from space, but we shouldn't really forget that we also equally need all this ecosystem of small and moderate-sized satellite and telescope from the ground, because it's really important both to study better all these targets, but also to be preparing our choices. And most importantly, I think, take more risks. It's really important sometimes, if you want to address a question that is particularly complex, to take some risks. And so in this idea of locating an ecosystem, I think that being able also not only to look at a government organization to fund these satellites that in many cases can be quite expensive and complex to build, but also looking at the private and commercial sector, in my view, again, is an opportunity that we all have to increase the number of potential facilities that can give us some great data for these questions that are important for the entire humanity. Thank you so much for your attention.